Right now, as you watch this video, Earth is fine. The sky is blue, the oceans are liquid. Somewhere, someone is having breakfast. This sentence is true, and it has been true for 4.5 billion years. But here is what almost nobody tells you honestly. Earth's end is not one single event waiting in the distant future. It's not a single asteroid, a single explosion, a single dramatic moment that scientists are watching for. It's a queue. A long, ordered list of ways this planet stops being able to support life. Some of them could happen in the next 5 minutes with zero warming. Some of them are mathematically guaranteed to happen on a precise timeline, whether humanity does anything about it or not. And the most unsettling part isn't any single item on that list. It's the order. Because once you understand the actual sequence, once you see how close together some of these threats really are, and how impossibly far away others sit, we're not waiting for the end. We are already standing in the queue. We're going to walk through the actual timeline in order, starting with the threats that could end everything before you finish watching this video, and ending with the one outcome that is not a possibility, not a risk, not a scenario, it's a certainty. Let's begin. Let's start with the most terrifying category on this entire list, not because it's the most likely, but because of one specific detail. If this happens, you will never see it coming. A gamma-ray burst is the most energetic explosion known to occur in the universe since the Big Bang. They happen when a massive star collapses into a black hole, or when two neutron stars collide. In the few seconds the burst lasts, it releases more energy than our sun will produce in its entire 10 billion-year lifetime. These bursts are directional. They fire out in two narrow, focused beams, like a cosmic flashlight rather than a light bulb. Most of the universe never feels them because the beam doesn't point at us. But if one did point at Earth, even from thousands of light years away, the gamma radiation would hit our atmosphere and trigger a chemical reaction that destroys the ozone layer. Not gradually, within minutes. Without the ozone layer, ultraviolet radiation from our own sun, the star that gives us life, would scorch the surface of every continent. Photosynthesis would collapse. The base of the food chain would die first, and everything above it would follow. Here's the detail that should unsettle you the most. Light from a gamma-ray burst travels at the speed of light. There is no warning system. No telescope on Earth could detect it coming because the moment we see the light, the radiation has already arrived. Some scientists believe a gamma-ray burst from 8,000 light-years away may have triggered a mass extinction event on Earth around 445 million years ago. The good news, if you can call it that, is that a star capable of producing a civilization-ending gamma-ray burst needs to be relatively close and pointed directly at us. Astronomers have cataloged the nearby candidates. None are currently aimed our way. But currently is doing a lot of work in that sentence. NASA tracks roughly 95% of asteroids larger than 1 kilometer that could cause a civilization-level catastrophe. That sounds reassuring until you sit with the other 5%. And it gets more uncomfortable when you consider objects coming from outside our solar system entirely. An asteroid doesn't need to be planet-destroying to end civilization as we know it. The asteroid that ended the age of dinosaurs was approximately 10 kilometers wide. It hit with the force of billions of atomic bombs, triggered global wildfires, and blocked sunlight for years. We are now reasonably confident we would detect another object that size years in advance. What we are far less confident about are the smaller ones, large enough to destroy a country and trigger climate disruption, but small enough that many remain completely uncatalogued, especially those approaching from the direction of the sun, where our telescopes are effectively blind. The Chelyabinsk meteor that injured over 1,500 people was only 18 meters wide. We had zero warning. Scale that up by even 10 times, and zero warning stops being a survivable inconvenience. Our sun is, by stellar standards, a remarkably calm star. That calmness is the only reason complex life on Earth has had the stability to evolve over billions of years. But calm is not the same as incapable. In 1859, a solar event known as the Carrington event sent a massive burst of solar material toward Earth. It set telegraph wires on fire and created auroras visible far from the poles. If an event of that scale hit Earth today, the result would be catastrophically different. Modern civilization runs on an electrical grid. A Carrington-level event could trigger continent-wide power failures and destroy critical infrastructure. Some regions could face blackouts lasting months or even years. And astronomers studying other sun-like stars have observed something even more alarming: superflares. Eruptions thousands of times more powerful than anything our sun has produced in recorded history. We still don't fully understand whether our sun is capable of one. In this specific area, we're working with an incomplete model of our own star's behavior. On April 13, 2029, an asteroid named Apophis will pass closer to Earth than many of our communication satellites. It will not hit us. Astronomers have ruled that out with high confidence. But Apophis matters for a different reason. It's a preview. When it was first discovered, it briefly became the most dangerous known object in the sky. Improved observations eventually eliminated the threat, but the discovery to elimination process took years. Years is not a comfortable margin. The honest statistical reality is simple. A civilization-disrupting asteroid impact is rare, but rarity is not impossibility. We are protected by probability, not certainty. Beneath Yellowstone National Park sits one of the most famous volcanic systems on Earth. A full-scale supervolcanic eruption would eject enough ash and sulfur into the atmosphere to trigger years of global climate disruption. Crop failures would not be regional, they would be worldwide. The reassuring scientific consensus is that Yellowstone shows no indication of an imminent eruption. The less reassuring fact is that Yellowstone is not the only supervolcano on Earth. Pandemics are different from every other threat we've discussed so far. They don't come from space, they come from us. Engineered pathogens, accidental releases, and increasingly connected global travel networks create risks that many researchers now rank among humanity's most serious near-term threats.
As the runaway greenhouse effect continues, Earth's atmosphere begins to transform. Water molecules in the upper atmosphere are broken apart by solar radiation. Hydrogen escapes into space permanently. The oceans do not simply evaporate, they leave forever. This is similar to what scientists believe happened to Venus. Over time, Earth becomes hotter, drier, and increasingly hostile to life. Eventually, the planet begins to resemble Venus more than the Earth we know today. Here's something surprising. The first life to disappear will not necessarily be the most complex. Plants may vanish before many microorganisms. As atmospheric carbon dioxide declines, photosynthesis becomes increasingly difficult. Without plants, food chains collapse, animals follow. But simple extremophile organisms could potentially survive for hundreds of millions of years longer. Life began on Earth as tiny, resilient organisms surviving in extreme environments, and it may end the same way. Approximately 5 billion years from now, the Sun will exhaust hydrogen fuel in its core. Its outer layers will expand dramatically. The Sun will become a red giant. Mercury will almost certainly be consumed. Venus will likely share the same fate. Earth's future is less certain. Some models suggest our orbit may drift outward slightly as the Sun loses mass, perhaps enough to avoid being physically swallowed. But survival is the wrong word. Even if Earth escapes direct engulfment, surface temperatures would rise beyond 1,000 degrees Celsius. Rock would melt. Any recognizable trace of the world we know would disappear. After the red giant phase, the Sun will shed its outer layers. A beautiful planetary nebula will briefly form around the dying star. At the center, a white dwarf will remain, an Earth-sized remnant of the Sun's core, slowly cooling over trillions of years. If any remnant of Earth still exists, it will orbit that fading ember forever, a dead rock circling a dead star. So, here's the complete timeline. Tonight, there is a tiny but real chance of an undetected asteroid or some other cosmic event arriving without warning. Within a human lifetime, there are risks capable of testing civilization in ways we are only partially prepared for. Within roughly 1 billion years, the Sun's increasing brightness guarantees the end of Earth's oceans and the collapse of complex life. Every living thing that has ever existed on Earth has lived within a remarkably narrow window of time. Dinosaurs, whales, forests, humans, all temporary. That doesn't make them less remarkable, it makes them more remarkable. Earth was never going to last forever. Nothing does. Not stars, not galaxies. Eventually, not even the universe as we currently understand it. The real question was never whether the Q exists. It does. The question is what that knowledge changes about today. If you take one thing from this video, take this. We have, by any reasonable estimate, hundreds of millions to billions of years before any of these guaranteed cosmic events become immediate problems for life on Earth. That is an almost unimaginable amount of time. The queue is real, but you are nowhere near the front of it. What you do have with absolute certainty is today. This one, right now. Make of that what you will. If this video changed how you think about the ground beneath your feet, subscribe to Void Atlas. We go further every week. I'll see you next time.